In this goal, we are going to be talking about neutralization reactions and titration. What is a neutralization reaction? This is when you take an acid and you add it to a base or vice versa, and you end up getting a salt and water. And also you will get a lot of heat. This is an exothermic reaction. So here's our example equation of a neutralization reaction. We have hydrochloric acid and we have sodium hydroxide, and the salt that we're going to get is sodium chloride and water. So water is one of the products that I make. Now, when you really look at this reaction, I can write the net ionic reaction. In other words, only include those things that are being produced by the reaction with no spectators. So let's pick apart our acid and our base and everything else that's involved in this equation. Now, before I begin, when I have my hydrochloric acid, this is in solution, so it is aqueous. And so I end up having hydrogen ion floating around and also chloride ion floating around. Remember, this is a strong acid, so it will have complete dissociation or ionization. It will fall apart. My base will do the same thing, and this is a strong base. So your first two groups on the periodic table, when they're put with hydroxide, they will form strong bases. So sodium is in the first column. It's an alkali metal. Put with hydroxide, I get sodium hydroxide, and it is a strong base. It will completely fall apart in solution, and it will yield the sodium ion plus the hydroxide ion. Now, when I look at my reaction, sodium chloride, it is a soluble salt. So floating around in the water, it is not going to be sodium attached to chlorine. I am going to get sodium ions and also chloride ions. And then the thing that I make in this reaction is liquid water. So that just stays together, just like that, with a little L there. Everything else is aqueous in solution. So when you look on the left side of the equation, on the right side of the equation, do you see anything that is not participating in making our water? Sure, we have some spectator ions. Sodium ion is on each side. So I can eliminate that for my net ionic equation. And also chloride ion is on each side. So it is just a spectator. So I can pull down everything that's left over. And so this is my net ionic equation, and this is for a strong acid and a strong base. It will always be hydrogen ion from the strong acid plus hydroxide ion from the strong base, and I will make water. There are also reactions if there's weak acids and strong bases and strong acids with weak bases, but I'm not requiring you to know those equations. The only one that I want you to know is when a strong acid and a strong base react, we get water in our net ionic equation. So hydrogen ion plus hydroxide ion yields liquid water. Now in the lab, we can use this neutralization reaction to help us determine an unknown solution. So maybe there's a solution that we find in the back and we don't know if it's what it is. Maybe it's an acid, maybe it's a base. I could take some litmus paper and I could test it out. If it turns blue, I know that it's a base. So I still need to know the concentration. Now that I know it's a base, I can titrate it with an acid and make a neutralization reaction. So an acid plus a base is a neutralization reaction, and I end up making liquid water. So titrations are used in analytical chemistry. It's a way to analyze some unknowns and get specific concentrations of what's there using something that you already know. So here's a few graphs that show this strong acid, strong base titration. And just as a reminder, our net ionic equation is making liquid water here. An important point on the graph is called the equivalence point. This is when the moles of acid equal the moles of base. So when I titrate my acid with my unknown base, I'm going to get a point where I add just one drop of that base and my pH will increase. So let's go through this graph right here. So starting off, I see that I'm a very, very low pH. So I'm starting off with an acid. I have an acid in my container, and I'm going to drip in my base. And as I drip in my base, you can see that the pH increases. We can see it starting to increase. Right about here, I see that if I add 1 drop of my base, immediately my pH is going to shoot right up. And that is because in my neutralization reaction, all of my hydrogen ion is going to be used up. So when I first start with it curved, when it's going up here, I have my OH being added and my hydrogen ion is getting used up. Eventually it's going to come to the point where I do not have any more hydrogen ion. So as soon as I add that extra drop of OH, my pH is going to shoot straight up. Well, the titration will end at this point. I can use a pH meter to see the pH shoot up, but I can also use an indicator dye. And that indicator dye will turn a color at this equivalence point. When the moles of the acid equal the moles of base, that is the equivalence point. Now, if you're not doing the titration, just looking at a graph, how you determine the equivalence point is you look at the portion of the graph that is going straight up, and you say, well, it ends about here and it begins about here, so you're going to go in the middle and read what that is. Now, if it is a strong acid and a strong base, it will always have an equivalence point of 7. So I know because my equivalence point is 7 that this is a strong acid and a strong base. Let's look at this second titration. This one I'm starting out as a base. So I'm dripping in my acid drop by drop, and as I'm doing it, I'm using up my OH. So this right here is using up the OH. Eventually I get to this portion where if I add 1 drop of my acid to my base, there's no more base to get to suck up that hydrogen ion, that acid. So you're going to see the pH drop really, really low with just 1 drop added. Again, to find that equivalence point, find where it goes straight up and down, go in the middle, and then read across to the pH. And again, we see our pH is 7, so we know that we had a strong base and we had a weak acid. Now, this lower part of the curve, we usually don't do in the lab. We don't keep adding excess acid. But in order to get this nice graph, we would keep adding acid so that we could see that it just gets more and more acidic. Now, reaching that equivalence point is hard to see. So I can use a pH meter, but sometimes pH meters don't give us instant results. We have to wait 10 seconds for the pH to adjust and to read it. So it's easier to use an indicator dye to tell us when we are at that equivalence point. So we want to pick an indicator dye that will change a color right very close to what the equivalence point is. So for example, if my equivalence point is 7, so that's when the moles of acid will equal the moles of base, I can use this pink indicator dye that will change color about a pH of 8. There are many indicator dyes. You actually can use other indicator dyes that are a little bit closer to a 7 to use. But this pink color we use often in the lab. But this pink indicator dye we use often in the lab. So what will happen is we'll add that 1 extra drop and we will go past the equivalence point and even past that end point. But it will be within 1 drop, which is pretty good results. So the end point is when I stop my experiment. When I see the color change, I will stop. My equivalence point, this is where the strong acid equals the strong base. The moles of the strong acid equals the moles of the strong base. And so I want these two to be pretty close together. All right, here's an example titration problem. So when I add that 1 drop and it stays pink for at least 30 seconds, even though I'm mixing it and trying to get the color to go away, then I know that I'm at my equivalence point. I can use this formula. The molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. Because my moles are equal to each other, then this is the equation. And this equation might be familiar to you because we've used it as our dilution equation. So when I dilute a concentrated solution, I add some water, I find that the moles of the concentrated solution are equal to the moles of the dilute solution. And because those molar amounts are the same, then I can use this equation. So now I put my acids on the left and my bases on the right, but it really doesn't matter. So you're going to find the two numbers that go together, and they're going to go on one side, and then you'll have just one lone number on the other side because you need to solve for the unknown. So I have molarity of my acid times the volume of my acid equals molarity of my base times the volume of my base. And these two numbers go together, and they are my acid, but again, it doesn't matter which side I write this on. And you do not need to be in liters. You can be in milliliters as long as you use liters on both sides. So I'm going to solve for my molarity of my base, and my volume of my base is 15.6. So I'm going to divide each side by that 15.6. And so the molarity of my base is 1.28 molar concentration. In class, we did an actual titration, so I could show you some of the lab technique, and I will try to post a YouTube video that shows a titration. All right, other titrations you might see besides just strong acid and strong base, you might see a weak acid and a strong base, or a weak base and a strong acid. Let's look at this first one. So it's a little bit pixelated, but I wanted you to see in comparison the strong acid. So my weak acid, you see that it starts a little bit higher up on the pH scale. But what's important is that equivalence point. So again, I'm going to look where the one drop makes the pH shoot up. And I'm just going to try to find the middle of that straight up and down part. And I see I have a pH of about 8.5. Notice this is above 7. So strong acid and strong base will always be a 7, but if it's a little bit alkaline or a little bit basic, I know I have a strong base. And then the other one will be the weak acid because, again, it's a little bit alkaline at the end of the titration. Let's look at this next one. If I have a weak base and a strong acid, again, I try to give the comparison for the strong base right there. And so our weaker base, it starts a little bit lower. We still have that straight up and down part where we add one drop and the pH goes down really fast. Again, you're going to find that equivalence point. I see that my pH, I'm going to say, is 5. So it's a little bit acidic. So this tells you have a strong acid mixed with a weak base. You also could have a weak base and a weak acid, but that is beyond the scope of this class. I'm not going to give you any of those. It's a little bit more complicated to figure out what you have. So your three types of graphs, you will have a strong acid and strong base, and you'll also have weak acid and strong base, and weak base and strong acid. And you could also have the reverse of all those. So really there's 6 that are there, but 3 different combinations. So go ahead and stop the video and see if you can figure out the combinations here. Are they strong? Are they weak? Do they start with a base? Do they start with an acid? And what is the equivalence point? Okay, let's do this first one. So we see that we are starting with the base. And I'm going to go to that straight up and down part. I'm going to go in the middle. I'm going to find my equivalence point. I see that it is above a 7, so this means that I have a strong base that I'm starting with. This is going to end up very alkaline. And then this is a weak acid that I'm adding to it. You can also see that the weak acid, it doesn't shoot down very low. It stays up pretty high. So that's kind of another clue that I have a weak acid there. Let's look at B. So at B, I'm starting out with an acid. I'm in the acidic range. So to determine if I have strong or weak, I'm going to look at that equivalence point. So go to the middle, and I see that I have a pH above 7. So that tells me that I'm going to have a strong base. So really it's just the opposite of A. And let's do C. So look at that straight up and down part. Look in the middle. And I have a pH of 7. So what does that tell us? I have a strong acid and a strong base, and I'm going to start with the strong acid because it's very low pH down there and a very high pH here.